Hello, YouTube. Let's get back to the business of finding the forward difference. So let's just recap what we did last time. We are trying to define an operator called diff, which takes one formula and spits out another formula. And I don't expect you to start this morning knowing how to define this operation. The point is that we're going to figure it out by looking at its specification. And this is its specification. It is telling us that we should be able to figure out what we have to add to evaluate Pn in order to plug the gap between it and evaluating P at the number one bigger. So we're asking how much bigger is P evaluated at n plus 1 than P evaluated at n. So we just want a formula that tells us the difference. And our strategy for figuring out what diff has to be was to start doing the proof before we do the definition. I mean, we figured out that we are going to need to work inductively over the structure of the formula. We're going to be taking the formula apart and applying appropriate rules to simplify the task of saying what the difference is. And then what happened? I don't know. Why don't you tell us what happened, Clemens, in the first case?
What happened in the first case? So let's see. So the first case was that P is equal to X. So we just have a variable, right? And then we needed to prove that if we evaluate X at successor of n, we get actually X at n. We get the difference of X at n plus X at n. So X at n, this is just n, whereas this is n plus 1. So the difference here should be the difference between n plus 1 and n. The difference between n plus 1 and n should be.
I mean, yeah, the amazing, not rocket science.
Should be 1, which is up
1.
here.
Right.
Which is kind of written here in a less familiar way, but it is 1.
Yes. The numerical constant 1. Okay. And then I'll do the next one. It's even easier because our formula is a numerical constant, which, because we were in a hurry, we just left the awful name that Ask chose. But I will put in a nicer name, and I might even just insert a tasty line break. And right. So what happened here after we did the test was that we were told whatever diff is, it had better not it better not be anything much, because whenever you add it to C, you better get C. So we pretty rapidly figured out that when our formula is a numerical constant, the definition, the difference between its output for one input and its output for another input, given that it ignores its input, is hee-haw. So the difference for numerical, when the formula is a numerical constant, the difference had better be the particular numerical constant 0. Everybody fine with these two base cases? And is everybody fine with the transferable kind of game that we are playing, where you, even if you don't know upfront what the definition is supposed to be, when you look at the story so far in the proof, you get goals like this one and goals like this one, and then your job is to choose the definition so that those goals are just true already. Okay, so this is, you know, yet another this is university, not school situation, where when you're doing school mathematics, that's been designed to enable mediocre mathematics teachers to teach to the test, and which is, there are fabulous mathematics teachers out there who find this experience as frustrating as I find it. You know, so correspondingly, you are in the situation where now we need that computer to stay exactly where it is. Yeah, you know, you're expecting that the drill and practice that your teachers put you through will enable you to react under exam conditions to the fixed repertoire of puzzles that the examiners are allowed to set you. And quite often I encounter students asking me, how dare you ask us something you haven't asked us before? And I say, welcome to university. You know, so here I'm giving you something which I expect you not to have seen before, but I'm giving you enough information to figure out what it is, and you have to be a detective and figure it out from the thing that you're trying to prove about it. Okay. I think so I mean, we're going to spend the whole of this lecture finishing this puzzle, if we're lucky, right? I'm going to try and take this super slowly. The case for plus is really very indicative of how to go about it. The case for multiplication is where the real challenge is. So first of all, I'm just going to change names because it's early enough in the lecture that I'm not panicking about it. So I've just, yeah. So we're going to look at the plus case, and I'm going to get rid of these awful QR, QR. I'm also going to put, yeah, it is dangerous. Now that Marx is quick enough, I feel it's important that we go back to sort of solidarity mode rather than so, yes. Right. Oh, the N is important, and I want it to be. Maybe you can slightly resize. Yeah. Right. And now I'm going to leave. I'm going to delete that and get asked to generate it again. No, with the good names. Did I foolishly? What on earth happened there? Did I do some? Did you reload it? I hope I didn't, because I just lost that bit of renaming.
The previous case, this balancing.
Yeah, I think I must have done an accidental back gesture, which is exactly what I did not want to do. Right. So let's see if we can get this behaving more nicely. Right. I'm going to delete this. I'm going to try not to press back. Instead, I'm going to try and press send. And that is more like it. So let's just move this prove here. Yeah, okay, I should hit accept first. Yeah, because it's this goal I want to focus on. Right. So this is where we're at. So let's think about where we can go from here. We don't know the definition of this diff of Q plus R yet. But here we can see Q plus R evaluated at N. And here we are at least talking about Q evaluated at successor of N and R evaluated at successor of N. So even though we don't know what the diff is, what can we do? Do we know anything useful that might enable us to make progress in this proof? In particular, what do we know about Q? And what do we know about R? They're smaller than P.
It's important to remember that this is part of the big induction.
Yeah. So we're entitled to assume that we already know the result for Q and for R. So we're entitled to, let's even do it. I recommend that when you're learning, it's not a bad thing just to write a little comment. That's the syntax for a block comment that says the things you know. So we know this, that we know the result for Q, we know the result for R. We know these things. So the game, as ever, is to ask ourselves, do we see anything we like? Do either of these, either the left-hand side or the right-hand side of these equations show up anywhere in our goal? Do you see an evaluate Q successor of N? Yes, you do. What? So you have the option to replace in the goal this evaluate Q successor of N with what we know inductively that it's equal to, namely this thing. Evaluate diff Q at N plus evaluate Q at N. You know that if you make that replacement when doing a by root, that you'll be able to justify that step. Then the question is it a sensible move to make, right? Not all moves that you know how to make are good moves. But would we like to see evaluate diff Q at N? And would we like to see evaluate Q at N? Look at the right-hand side of the goal. we know it's not going to be the end of the story, but we would like to, we like those pieces. We're recognizing pieces that are useful to us. And we also would like to see and evaluate diff Q and then evaluate diff R, because we know we can define diff of Q plus R in terms of diff Q and diff R. So basically, the plan is to massage things so that we make this thing show up as part of what the difference has to be, or what the thing has to be, and then whatever this is has to be whatever's not accounted for. Okay. So putting that idea together, the most important thing is to remember to delete the question mark, which is the thing I always forget to do, and to spell by with a lowercase b. And to remember that we want something in parentheses. And I'm just going to put in lots of extra brackets that we might care about, possibly even extra spaces. So I want the right-hand side of each of the induction hypotheses. Right. So what I'm expecting when I press send is that I will get one sub-goal that follows using just under plus to dig out the two separate pieces of this sum that follow by the induction hypothesis. So okay, I'll hit send, and then I'll hit accept. And now let's just go look what happened. Again, I'll just try and pull this out. Okay, so you can see that our first sub-goal is indeed, so from the left to the middle is indeed something that is directly coming from the induction hypotheses, which is how we chose it, and which will follow by under plus. If I could only find my cursor. So that's not where the real puzzle is. That's just as expected. Meanwhile, you've got these bits and pieces. So I'm going to press sand just to get that under plus thing out of the way. Then I'm going to hit accept. So so this thing was just using the induction hypotheses to justify the move we made, and now we're at the bone. Okay. So you can see that here, if I put the bracketing in, which is this way, is the bracketing, you can see that on the right-hand side of this equation, we've got evaluate Qn plus evaluate Rn. And on the left-hand side of the equation, we've got those pieces separately, along with some other stuff that is going to have to be what the difference, that's going to have to tell us how the difference is defined. So at this stage, we're going to make use of what we know algebraically about plus, right? We know that plus is associative and commutative. We can regroup the bracketing. We can reorder the things we're adding up. Let's have a look at what sort of stuff is knocking around in the library functionality, in particular. If this is a particular weaponization of being associative and commutative, namely that when you've got 4 things you're adding up in 2 groups of 2, you can swap the ones in the middle. And this is what we need to do here, because on the left-hand side of the equation, we've got them grouped in terms of what's to do with Q, what's to do with R. And on the right-hand side, the grouping is what's new, what's old. So if we swap the middle 2 on the left-hand side of this goal, we'll group the left-hand side in terms of what's new, what's old. So you can see I'm trying to get evaluate Qn closer to evaluate Rn, because that's what I've got on the right-hand side of the goal. So the game at this stage is, what algebra do I know that might move the pieces that I need to be nearer each other? So I'm going to do another by root. Oh, I think I'm going to do another by root, this time swapping the middle 2 of 4. So I'm going to take this left-hand side, copy it, paste it, and then mangle it. Right. Okie dokie. Oh, what did I? Oh, I didn't. So I've got those things. Yeah, I just need that. Okay, thanks. So hopefully that's a step I can justify. And let's see. What have we got? Cool. We get one sub-goal because left to middle was already justified. And we're nearly at the point where I'm going to hand over to you, Clemens. I don't think it should be that big a challenge. So now you can see that we've got the left-hand side of the equation and the right-hand side of the equation have the old stuff, the value at n, same place, same shape. And the only things that are different left and right are the things that are talking about the definition we don't know yet. So we're ready to do an under plus move, and we'll wind up at a goal that is going to give the game away. And I'm going to have the game, and I'm going, and I want the game to be given away to Clemens. So you can see after, you need to press accept first. And then I'll just rearrange this piece of business. Right. We are at the stage where we have chopped away all of the stuff that related to the value of Q plus R at n, and we're left with an equation that's got diff of Q plus R on one side, and separately diff Q and diff R on the left-hand side. And our mission is to define this thing in such a way that this equation becomes true. So this equation is, I'm hoping, a massive clue. So Clemens, why don't you finish the definition and make that goal disappear?
Excellent. Okay, indeed. So we have this equation, and so now we have to choose just the definition of diff q plus r in such a way so that it holds. So basically the difference of q plus r should be somehow the difference of q plus difference of r. Difference of q is of course a formula, and the difference of r is also a formula. So therefore we go up to the definition. Oops, where's the definition? We go
long time.
Long.
Yeah, and we should rename them.
Oh, sorry. Where am I?
No, we're having another people's computer issue.
Indeed. Let's go here. Q. And be careful not to touch too many buttons at the same time.
Yeah. I think I accidentally did a sweep back gesture, which caused a reload at exactly the wrong moment.
So we want something so that the difference of Q plus R evaluated at N is equal to the difference of Q plus the difference of R, both evaluated at N. So we just do the following. Good. I hope this is not a big surprise at this stage. So now let's move to send and see what happens.
It's defined.
It is
what's happened in the proof.
Wait, is it defined? Why does it say? It is defined. Okay, 1 second. I need to accept it. Let's first accept it and then we discuss further.
Yeah, it should be.
It's already accepted. Okay, accept is instant.
Yes,
no.
It's, accept just works in the client.
Yeah, it works, but it doesn't work if I don't press. Sorry.
Yes.
Sorry, 1 more sec. Now it is defined. Oops.
Yeah.
It's
something needs to see. Yes, and all of a sudden.
Here.
Yeah.
So now this whole thing is commented out, and asks us, why did you ever bother?
Now that you've made the definition, that's just obvious. Yes. Okay, I'm paying attention to the time. And I can see that we are not going to get multiplication out the door. So I think we should just have a think about it. How about that? Which means that I should stop sharing this screen. All of this, I will publish this code. And I'm absolutely fine with doing this the slow way. So I'm going to replace pin. So now we've got but now I'm going to switch to document camera and wait. Right. My collection of Sharpies. Yeah, it's cool. Okay. So let's have a think about multiplication. Right. Because so far you've found that the difference of x is 1 and the difference of a constant is 0 and the difference of a sum is the sum of the differences. And you heard me last time promising you that this is not the notion of derivative that you learned in high school. And yet, so far, it's been exactly the same as the derivative you learned in high school. This is to lull you into a false sense of security, but it also because it's in the multiplication case that the difference is gonna show up. I mean, the difference between the two ideas. Okay, so let me draw a picture of why that happens. So I might need to just abbreviate things. So when we do this, it'll be the same deal again. We'll have something about evaluate Q at successor of n and something about evaluate R at successor of n, say. So we'll have, let's suppose, let me just write ev for evaluate. Let's suppose this is ev Q at successor of n. Our induction hypothesis tells us that we can split that up as evaluate Q at n and evaluate, and because it's a piece of paper, I'm going to write diff like that, diff Q at n. We're saying we've got these two pieces. And we've got the same thing for R. So this whole thing is evaluate R at successor of n, and splits up as evaluate R at n and evaluate diff R at n. So what difference are we trying to actually compute? Right. Do I have a purple pen? Of course I have a purple pen. Right. So the value of Q times R at n is given by this rectangle, the area of this rectangle. Is everyone happy with that? That if we multiply evaluate Q at n by evaluate R at n, we get the area of this rectangle. Cool. And then if we evaluate Q times R at successor of n, we get the area of the big rectangle. And what we would like to see is that we need to figure out that we can see that the difference is going to be the sum of these three smaller areas. Now, back in school, you may have been taught differentiation from first principles or something like that. You'd be figuring out what's the derivative of a product, and you'd find that if you take some little step size delta, then the area of this thing in the corner, this piece in the corner, is expressed in terms of delta squared and becomes negligible as delta tends to 0. So that's to say, when you're doing infinitesimal differentiation, this rectangle in the corner doesn't matter. Its area is as near to nothing as makes no difference. Whereas we are choosing our step size to be 1. We are seeing the difference in what comes out when you make a difference of 1 to the input. So you are going to notice this rectangle, and that's where the difference is going to be. So we're going to need to figure out how to deal with this. You can still see that we're going to have, you can see, you might recognize what are the dimensions of this rectangle. This rectangle is of height R and of width diff Q. So this is one of the pieces you're used to. This rectangle is of height diff R and of width Q. So this is the other piece you're used to. But the trouble is that this thing in the corner here doesn't go away. And let me show you more concretely. I did mention it last time, but more concretely, a very specific example, which is if we were working with just the formula x squared, then suppose this is 5 by 5, and then this is 5 by 1. So the whole thing is 6 by 6. Then you can see, so you're used to the derivative of x squared being 2x. There's your 5 plus 5. That gives you twice 5. But this 1 in the corner is not going away. And the difference between 5 squared and 6 squared is 11, not 10. So the difference between x squared and x plus 1 all squared is 2x plus 1, not 2x, because this 1 in the corner doesn't go away. So we'll need to figure out, when we cook up a formula to describe what this difference is, we'll need to adjust for that extra little blob in the corner. And what I'm actually going to propose to do, but I'll leave it as a cliffhanger, is to collect this rectangle and this rectangle. That's my shut up alarm. So how am I going to get my hands on this rectangle? Well, you may remember that a little while ago, we introduced an operator called shift. Which satisfies this equation. So I'm able to get from this width to this width either by adding 1 to the input or by shifting the formula. So we'll be using so the difference will turn out to be that this rectangle is shift q times dr or diff r. This rectangle is diff q times r. So we figured it out on paper. Next time we'll bully it into ask. All right, folks. I think that's a good place to stop. I will make sure that these pictures don't go missing. I will get all the code online, and I'll get this video on YouTube as soon as possible. Cheerio, YouTube!